Hi, this is Minglun Gong. I'm a professor and director for the School of Computer Science, University of Guelph. It is my pleasure to introduce our work on novel network architectures for arbitrary image style transfer. This work is a result of a collaboration with Zhi Jie, Chunjin, Yang, and Hui from Shenzhen University. Given a content and a style image, the arbitrary style transfer studies how to extract features from these two images and then fuse them into a novel image. Hence, the content image can be easily stylized using different style images. The pioneer work in this area was developed by Gittes et al. In 2016. They demonstrated that multi-level feature statistics extracted from a pre-trained CNN model can be used to separate content and style information, making it possible to combine content and style of arbitrary images. More algorithms are designed for this task afterward. Some are based on matching global statistical features, whereas others combine local and global style pattern transformations. My collaborator and I proposed two novel network architectures for style transfer. Here I first introduce the Exchangeable Feature Alignment Network, which has been published at AAAI this year. Our observation is that previous methods tried to extract content and style features directly and independently. As a result, they often produce various distortions in local style patterns and global content structures. Hence, our goal is to joint analyze style and content image pair and then extract exchangeable features for better synthesis result. More specifically, for each image pair, we first extract their content and style features. We know the style and content features from the same image are compatible, hence we use common information to align the two style features and obtain exchangeable style features. Finally, we use the exchangeable style feature to fuse with content. Based on this motivation, we designed such an autoencoder framework. The core part is the Exchangeable Feature Alignment module, or the EFA module. We also integrated multi-scale strategy in our framework to handle features and their different scales. Here is the network structure of EFA module. We first feed the style features into a feature exchange block to extract their common information. We then use the common information to align the original style features to obtain exchangeable style features for fusing with content. Here is a detail of the feature exchange block. Given two input features GC and GS, our goal is to compute their common feature GCOM. To do so, we also compute a unique feature for each of the input feature vector and require the common feature to be orthogonal with each of the unique features. We further require that the original feature vector can be reconstructed from the combination of the common feature and each of the unique features. The loss function is computed using input, content, and style image pair and the synthesized result. The definition is the same as Gittes' paper. Now let's see the experimental results and comparison with existing approaches. Thanks to the alignment of style features, our results provide richer colors, maintain better texture consistency with style image, and better preserve structures in the content image. Here are two more sets of experimental results. Based on additional masks, we can synthesize different styles for different regions of the content image. The second network I will discuss is called Error Transition Network. The corresponding paper was published at NeuroIPS last year. We observe that existing approaches, including our own approach discussed above, try to generate results in a single shot. When the content and style images differ too much, the result generated may be distorted. Our goal is to gradually refine the stylization result using an iterative error correction mechanism. This example illustrates the effect of multi-step refinement. The top row shows the zoomed-in view of highlighted areas. We can clearly see that the result gradually approximates the style image. Our approach starts with a zero vector to represent the initial stylized image. The zero vector is fed into ETNET together with downsampled input content style image pair to generate a residue image. The sum of the residue image and initial result gave us the updated stylized image. The new result is upsampled to be used as initial image for the next resolution level, until the full resolution result is obtained. Here is a design of the error transition network. Its goal is to compute a residue image based on an intermediate result. Two encoders are used. The first one extracts deep features from intermediate result. The second one takes content and style images as input as well to compute content and style error. We then fuse content and style errors into full error feature delta E and determine a compatible residue feature delta D. Finally, delta D and delta E are fed into multiple residue propagation blocks to obtain residue image. Here are the details of residue propagation block, which consist of upsampling and concat operation, as well as multiple convolution layers. Here is the loss function, which again is same as Gatti's paper. The experimental results are shown here. We can see that ETNET can better preserve large-scale structures from the content image and mimic the patterns from the style image. We can see more details from this figure. Only our approach captured the oil painting texture from the style image. Again, we can apply different styles to different areas of the content image. Two approaches are discussed here, EFANET and ETNET. If you wonder which works better, here is a comparison. ETNET produces a bit better results, but require more computational cost. In conclusion, we presented two novel network architectures for arbitrary image style transfer. Each algorithm is based on one simple idea. The first one is based on the observation that the style features extracted from the style image may not be compatible with the content features extracted from the content image. Hence, we jointly analyze both style and content image pair to extract exchangeable features. The second network is based on the observation that generating stylized image using a single shot may not produce optimal result. Hence, we use a self-correcting model to predict the errors and refine them accordingly in an iterative manner. That's all for my presentation, and thank you for joining us.